So first off, thanks for coming. It's the last talk, I know. I guess you all are already hungry and want to go home anyway, but I hope this one will at least be a little bit entertaining and show you a little bit why I think Netty is a good framework and why you probably should use it. So the title of the talk is a little bit provocating, I guess. It's called like one framework to rule them all. It's not like that I think that all frameworks are bad except Netty. It's more like that most of the times you may even use Netty and don't know it because many frameworks and network frameworks are built on top of Netty already. So if you, for example, use WordX, use Netty. If you use something like Play, use Netty. If you use Cassandra, use Netty, and so on and so on. So I want to show you a little bit about the internals and why I think it makes sense to build something on top of Netty. So first off, something about me. My name is Norman Maurer. I'm leading the Netty project. So I started to work on it like 5 years ago, or 6 years, and leading it now for about 1.5 years. I was just selected as Apache Cassandra MVP, which basically means some very valuable person, whatever that means. I wrote a book on Netty, so if you want to support me, buy it. I'm a member of the Apache Software Foundation and also a committer in the Eclipse Foundation. So first off, I want to talk a little bit about Netty itself and how it evolved over the time. So it was a very, very long journey since then, and I hope it will go on for a little bit longer. So Netty 3 was released in 2008, which doesn't sound too long ago. I mean, it's 8 years. It's still a long time, but basically, it was started even before this. So it was started like, I think, 13 years ago, which is a long time. Netty 4, which was the first new major version, was released like 3 years ago, which had very different APIs and different characteristics, like in performance and all that kind of stuff. I will talk a little bit about this and what we changed to make that happen. Then we released Netty 4.1 this year, which basically means, or provided on top of what Netty 4.0 would provide, like HTTP2 support and other protocols, which I think are very important these days. It's one of the most used network frameworks for the JVM. So if you don't use NIO directly, most of the people use Netty, or a framework on top of Netty. It was founded by Justin Lee when he was still Studi. He works now at Line these days, which is a big messenger, a company which builds a big messenger app for Asia. And it was first a JBoss project, and then it got independent. So basically when Justin Lee left Red Hat, it got, well, outside of Red Hat and is now standalone on GitHub. So Netty 3. I mean, Netty 3 works pretty good, I think, in general, and it's still widely used. But it has a few problems that we kind of solved in Netty 4 or made less worse. So first off, Netty 3 created too much garbage. What does it mean? So basically, we're creating too much objects, which some people may think is not a big deal because the garbage collector will just collect them and all that kind of stuff. But if you start to push stuff pretty hard, it can become a very, very painful thing. We made too many memory copies. So basically, what happened in Netty 3 was most of the times you allocated something, then basically on the heap, you get a heap buffer, then you want to write on the socket, so we do a memory copy to direct memory to hand it over to the socket. So we do a lot of memory copies. It has no good memory pool included. Why is this important? Because if you want to write high-performance network applications, most of the times you want to use native memory, like direct memory, which is expensive to allocate and also expensive to deallocate. I will talk a little bit more about this, why it's expensive and why you need a pool to make it work. It was not very optimized for Linux-based OS. What does that mean? I mean, you think like Java has an NIO abstraction which works on Windows, on Linux, on OS X, on whatever, which is fine. But sometimes you want to have like the last person of performance or even want to have features which are only there on Linux. And Netty 3 didn't provide this because we was just using the NIO abstraction. That changed a little bit on Netty 4. And the threading model was not really easy to reason about. Why was this the case? Basically, in Netty 3, every time you wanted to read something from a socket, we did this in a non-blocking fashion. So we had like a thread which runs in an event loop, basically, and just whenever some socket or file descriptor is ready, we read some data from it and then pass it through the pipeline, where you can basically do all the processing, transformation, all that kind of stuff. When you write something, we basically write it through the pipeline again until it hits the socket and then write it through the system call, to the network, to the kernel space and the network and all that kind of stuff. The problem here was really that inbound traffic or inbound processing happened in the event loop, so always in the same thread. But for outbound, for writes, that was not the case. So basically, always this was done in the calling thread, which means it was very, very difficult to reason about which threads operate on which data in which sequence. So we changed that in Netty 4. I will also talk a little bit more about this, how we did this. The problem here really is it worked pretty good. So Netty 3 is still used and people don't upgrade, which is a pain for us because we needed to maintain it. We just stopped to maintain it, so Netty 3 is end of life since like 4 months, I think. But people still use it because it just works. So please upgrade. So Netty 4 now, we create less garbage, which means the garbage collector doesn't need to run so frequently. I will talk a little bit about this later, how we do that. We have optimized transport for Linux-based operation systems. We use that by doing JNI. I will talk about this as well a little bit later, because JNI is fun. We have a high-performance buffer pool, which is based on the jmalloc paper. So basically, we re-implemented jmalloc in Java for direct memory. And it has a very, very well-defined threading model. Everything like inbound and outbound happen always on the same thread, so you don't need to care about synchronization, which is great. So it's really very easy to write your stuff. It's more like Node, I would say, but with better performance in Java. So to give you a little bit like an idea how Netty works, this is how the concept works of Netty. So in Netty, you have a channel. The channel itself is basically like the abstraction on top of the socket. So you can do a write, which goes down to the socket. You do a write or write EV, syscall, and pass data. Then you basically have remote address, local address, and all that kind of stuff. So all the information. So basically, it's like a connection if you use TCP. Then with each channel, you have a channel pipeline. The channel pipeline is basically just a doubly linked list of different channel handlers, which contains channel handlers. The channel handler itself can process inbound and outbound events. So what this means is basically every time an event which is inbound, which maybe, for example, we just read some data, a new connection was just accepted, this kind of events. When this happens, basically we start on the head of the pipeline, walk through it, pass it through each channel handler, where you can basically do something with the event if you want to, like you could log a new connection. You can transform bytes to a POJO. You could whatever you want, basically. If you do an outbound operation, like a write, we start at the tail of the pipeline and flow from the tail to the beginning, to the head, to the channel, and once we reach this, we basically do a syscall. This allows you to basically implement like an interceptor pattern, where you can do all the processing logic, business logic, just in pipeline reusable parts. So you could use this, and we use this way in Netty to basically write a codec for a network protocol. So our HTTP codec is basically a channel inbound, channel outbound handler, which means once we wrote this, if you want to support HTTP, you just put these two handlers in the pipeline, you're done. The same is true for SMTP, for Storm, for whatever. So the whole magic from transforming bytes to some POJOs that you can handle happens in the pipeline. There's also other interesting stuff that you can do. For example, you could count connections, close them, metrics, all that kind of stuff. And all the frameworks that use Netty built on top of this. For example, Finagle is using this to do all that like server filter chaining. Vertex is using that to dispatch that to their buffer handler or body handler and all that kind of stuff. So you can do a lot of interesting things here. And to give you a better example about it, basically it's just like pipes. If you ever use Unix, it's like pipes, but in both directions. So you can just chain different commands and alter the output and get something at the end. And you can do that inbound and outbound in both directions, basically. So garbage. So I want to talk a little bit about garbage collector and why it's a problem. So the cat is a garbage collector. The kid is basically your process that runs away because the garbage collector wants to do all the kind of stuff all the time. So what we did in Netty 3 was basically each event or each network event was a POJO, which made it very easy. So basically we only had like 2 methods. For inbound we had like something which was called upstream event or handle upstream event. So we just passed in a POJO, did some instant objects and know like this is a message event, this is a connect event and all that kind of stuff. The same we had for outbound. This is a write event, this is a connect event, and all that kind of stuff. The problem here was really every time you wanted to do a network operation, you create a new POJO only for this, even without creating one for the data, transforming, and all that kind of stuff, which sums up pretty heavily if you handle a lot of concurrent connections. Even worse, it's not very easy to optimize this for the JIT or for the JVM, because you're calling the same method with different POJOs all the time, do all kind of instant objects, which may, well, have a very complex class hierarchy and all that kind of stuff. So it's not very friendly. The other thing that we did for help with this, we introduced a very lightweight object pool. I'm not saying that you should do that. Only do that if it makes a lot of sense. Don't pool every object. But there are a lot of objects in Netty that we reuse all the time, or that we only use for a very limited subset in the same thread all the time. For example, if we have codecs, we want to transform bytes to multiple objects and put it in the list. We don't need to allocate a new list all the time because the lifetime is very limited. We can just basically store that and reuse the same thing again later. The same is true if we do did the POJOs before to call the method, if we now have replaced it with direct method calls that we have now. So basically each event is now we have a generate method, which basically is called every time you read something from a network layer. Then we have a channel active, which is called every time a new connection happens. We have a channel inactive, which is called if the file descriptor closed and all that kind of stuff. So you can make a big impact if you just save a few objects. And there's just like a week ago, there was a very interesting issue opened up at Netty where basically Twitter was testing how much difference it makes to either use this small object pool or not using, let's just garbage collector, do it a lot, and they said it's 4 times more CPU to not use the object pool for the use case. But we even allow you to basically disable it if you say I want to just have the garbage collector do everything for us. Yeah, like I said, we use JNI. I know most people hate JNI. I also kind of hate JNI, but I do it so you don't need to do it. So there are sometimes things that you can only do with JNI, at least at the moment. So for this kind of stuff, it makes a lot of sense. So the problems here really is, if we talk, for example, about the NIO, Java NIO package, which are basically the socket abstraction, it's very general purpose, which is a good thing, right? Because it should work on every platform and all that kind of stuff. It should work with every threading model and all that stuff. We don't care too much about this in Netty to some extent because we have, for example, a very well-defined threading model. So we know which thread will call something on one socket. We want to support advanced features that you don't get on the JDK at the moment. And I will show you some of the features in a few seconds. We can directly operate on pointers for buffers. So we basically can get the memory address, pass it over, which is a lot cheaper than just pass over object, for example, and do a lot of interesting things. And everything like this is built for you. You just include the jar and it works. At the moment, it only works on Linux. So we only have extra transport for Linux, which are optimized. Yesterday, a buddy of mine just opened another PR to support the same for OS X, for KQ basically. If you are on Windows, you can still use NIO. The API is the same. It's just hidden from the user. It's just another dependency that we basically provide. And here you, on the left side, you basically see the code switch from one to the other. The first one is using the NIO. So what you see here is basically you have a bootstrap. So that's a client. You bootstrap a client. You set the group. That's an event loop group. The event loop group basically it's like a thread pool, which has a lot of threads, which basically process different channels, which are assigned to them, like processing events per connection. You say, I want to have an NIO event loop group. Then you say, I want to use the NIO socket channel class, basically. So this is telling it, use NIO, Java NIO. If you want to use a native transport and you are on Linux, you can just say exactly the same and just alter 2 class names, basically. And that's it. It's getting a little bit harder if you use features which are only provided by the native transport. Then you cannot change so easily anymore. But you could change to the new KQ transport once it's merged. So what do we provide in the native transport to make it interesting? I'm not sure how many of you know about all the network socket options that are listed there. So I will explain a little bit what they are doing to give you a better idea why it makes sense to use them. So there's SO reuse port. It's completely different to SO reuse address. So SO reuse port let you bind to the same port multiple times with different threads, basically with different sockets. Why you want to do that? Basically, you let the kernel and the operation system handle for you the load balancing between threads, which is super nice. So if you have an application which needs to accept a lot of sockets concurrently, using only one thread may be a bottleneck because you cannot accept fast enough. And then basically the SO backlog that you can set get populated, the queue get too long, and then basically everything just times out. So you could fire up like 4 threads and let all the 4 threads basically accept different connections on the same port. Another very, very interesting thing that you can do with that is if you write in DNS server, you could accept datagram packets on the same port with multiple threads. That was actually the use case for which it was developed first by Google, I think like 4 years ago when it was merged in the kernel. But you can do a lot of interesting things with this. So this one is very interesting. You could even start the same process multiple times and bind it basically to the same port. The only problem here with Java basically is that you would need to reserve the heap multiple times. So it may not work out too well, but there are use cases. TCP Cork. TCP Cork allows you to basically send in a performant way, like, for example, if you have HTTP, you would have the headers in a buffer and the content in a file, and you could send it like with very efficient with only one round trip both together. So that's super nice if you want to basically serve files. TCP not send LOVAT is mostly useful, for example, if you use HTTP2, so you can basically tell or give the kernel a little bit of a hint when it should buffer data and how much before it really flushes it through the network layer. TCP fast open. TCP fast open is very interesting if you have full control over both sides of the connection, like the client and the server, because if both support, you can basically, in the first handshake, you can already send data. If you use this together with SSL, you basically can save a round trip for the handshake. But it only works if you have full control over both sides. So if you, for example, have the client app and the server app and both running the same data center, but you still want to use SSL TLS, that's a super interesting feature because it can really reduce latency. And TCP info, I think, is a not very well-known feature of Linux. It's very old, actually. It's very interesting. So with TCP info, you can basically get metrics on a file descriptor. And I think it's 32 different metrics, basically, so you can get everything that you never wanted to know. But also interesting stuff. So you can get, for example, metrics about round trip times, errors on the network interface where the file descriptor is on, and all that kind of stuff. And what you can do with this kind of things is very interesting things. For example, you can write a TCP client connection pool and can choose the connection based on the round trip time to the host that you want to talk to. So that's super interesting. I mean, it's very advanced, but you can do a lot of stuff. They are also like, you can do health checking stuff and all that kind of things. If you're really interested about what you all can do about this, just type man TCP, and in the man page, it's described everything. It's basically, we just pass through what Linux provide. So everything that you read here, you can read up in the man page and get more details about this if it's interesting to you. And another nice thing about this is because we can act directly, or because we call directly in JNI and just pass over like memory addresses, we don't need to create too much objects. But we can do that because it's very isolated. So everything of this is hidden from the end user, which is nice because it's very easy to crash the JVM if you do something horrible wrong with memory addresses. And JNI, especially JNI, it's a lot of fun to crash the JVM all the time. Buffers. Yeah, I want to talk a little bit about buffers. So I guess hopefully most of you have used byte buffer before. How many people like byte buffer? So either no one is using byte buffer or no one likes it. Okay, so the problem with byte buffer is really the interface. If you ask me, it's not very user-friendly. Because why? First off, you only have one index, a position basically, and a limit. And if you fill a buffer to read it, you basically need to flip it before, which basically sets the position to 0 again and the limit to where the position was before, and then you can read it. It's very easy to forget this. So whenever you debug an application which uses byte buffer and you wonder why you don't write anything on the network to a socket, probably because you didn't flip the buffer. Another thing about byte buffer is it doesn't ship a lot of utility methods which are useful. For example, if you write network protocols or network applications, you need to iterate over all the bytes in one buffer. Doing this with byte buffer is super expensive for multiple reasons. First off, every time you do a get, it does a range check, right? So basically it checks like, if you access index I, is it between position limit, whatever, right? So that can be super expensive if you do a lot of them, like iterating over, I don't know, a buffer with 10,000 bytes, for example. In Netty itself, we have our own buffer implementation, which helps you with these use cases. So for example, we have something which we call for each byte, which allows you to basically pass in a byte processor which is called until you return false. So basically every time it just gets the bytes in, 1 byte every time. When you return true, it keeps continuing the loop. When you return false, it's done. So we only need to do like the index check 1 time, which can make a huge difference. So when we introduced this, for example, we had before using just like get byte, get byte, get byte in our HTTP implementation, and we used this, it was like a 20% performance improvement just to switch to something like this, because we need to iterate over a lot of bytes. Then what we have in Netty and byte buffer is we have different indices for reading and writing. You don't need to flip. Basically, if you write, the writer index increase. If you read, the reader index increase. Once both on the same position, you cannot read anything anymore, which I think makes sense. Byte buffer itself, you cannot extend byte buffer in the JDK because it has a package private constructor, which sometimes can be painful because if you want to basically have a view on multiple byte buffers, it's not possible. Basically, if you say, well, I may have multiple byte buffers, you need to pass in an array of byte buffers and need to iterate over them by yourself, do all that kind of stuff. In Netty, we basically have a composite byte buff, which allows you to wrap multiple byte buffs but have the same abstraction over them. So you just operate on the same abstraction as before. It just serves you with multiple, well, extra methods, like you can get a byte buff at a specific index and all that kind of stuff, or you can add new ones to them, which makes it super easy to say like, okay, now I want to compose a packet of 3 byte buffs. Just wrap them, API is the same. The bad thing about byte buff in Netty is it's reference counted. What does that even mean? You need to basically release them. So you're writing Java like you write C, which sounds scary. It's a little bit scary. So let me first explain you why we are doing this. So what is Java doing? So if you want to write to a socket, you basically need to have a direct buffer which is off heap, which means it's native memory. At some point, this native memory needs to be released, right? Because otherwise, you will get out of memory. So Java itself tries to give you the illusion that you don't need to care about this kind of stuff, which is nice. That's why we write Java, right? We don't want to free stuff or manage our memory. The problem really is here, just think about what I said, it's handled by the garbage collector. The garbage collector runs once you're short on heap memory, but we're allocating outside of the heap memory, which means it may never run, may run too late, or if you're lucky enough, it runs, well, in a good time frame. So you have no good idea about whenever something will run to free up your direct memory. And now comes something really scary. If you want to have a little bit of fun, check out the OpenJDK, look into the allocation, deallocation paths of direct memory, of direct byte buffers. So first off, what they had, I think they recently changed it in Java 9 actually. So if you want to allocate direct memory, it needs to go to a static synchronized method. That's because they want to keep track how much direct memory you use, because there's something like max direct memory that you can specify in the command line, and once you go, well, over it, it basically throws an out-of-memory exception or out-of-memory error. But it's static synchronized. What does it mean? If you have a lot of threads which basically allocate together all the time, which is very, very often the case if you write network applications, then everything will just block each other. That's bad. Now comes the deallocation part. So the deallocation is also static synchronized, which is also bad. If you run short on memory, now comes the catch. It does a thread sleep 100. Well, first it calls system GC to tell the GC now it's time to run. Then it does a thread sleep 100 and says now, okay, now I waited 100 milliseconds and now I will try it again to allocate. Which means you could have a 100 milliseconds pause when you allocate, which is super bad if you write something which is kind of latency sensitive. You may say, well, if it's latency sensitive, you should not write in Java, but that's not true anymore. But 100 milliseconds pause for this kind of stuff could be horrible in production. So that's why we do reference counting. So what we do in Netty is basically, if you allocate something, you get a byte buff, it has a reference count of 1. Once you're done with that, you call release. Then it gets a reference count of 0. You can also call retain, which means it gets incremented by 1. So it can pass it along, this kind of stuff. So typically like you would do in C, basically. Once it's 0, we deallocate it for you. What we do with native memory is basically we get a reference to the cleaner. Don't do this. Don't do that by yourself. So we get a reference to the cleaner, call the clean method, or in Java 9, the run method, and then basically this one will call, well, all that kind of deallocation code that the garbage collector normally does. That works out kind of good. The problem still is it's static synchronized. So you still have the problem. So now we have two solutions for that in Netty. The first solution is basically use a memory pool, which I will talk a little bit about later. Which means every time you call release and the reference count goes to 0, basically you put it back in the pool and you can reuse it. So it will never go to the static synchronized stuff. But you need to keep the memory, right, in your pool, which is fine. Or we can also, if we detect you have unsafe, we can allocate memory by ourselves and don't go to the static synchronized blocks, because we can also call free by ourselves. The only downside here is that basically not the same limits will be restricted that you set with a max direct memory on the command line, but we provide different ones. So it's a trade-off. Because it's hard to get the releasing right, I mean, if you ever did C, you know it's sometimes hard to free all the time, you forget it, all that kind of stuff, and it's very, very hard to debug this kind of stuff. We have a leak detector in Netty. How did we do that? So basically what we do is we have different leak detector levels. Default is simple, which basically means we will enable leak detection in 1% of all your allocations and take a stack trace basically every time you allocate and every time you call release. So if something leaks, we can tell you, here you basically allocated it. So just check what you do with a buffer, and then you need to find where you need to deallocate. That can give you kind of a hint, but it's not very helpful most of the times. We use phantom references for this. So basically we just wrap it into a phantom reference, do it in a reference queue, and then we just poll it. If you see something like this in production, you should still use this in production. If you see this, basically you should enable advanced mode. What does it mean? Advanced basically take a stack trace on each allocation and deallocation for each buffer. So it slows you down a little bit, but you have a better idea. If that still doesn't help to find it, you can do paranoid. Paranoid takes a stack trace on each operation on the buffer. It's super expensive. So if you do that in production, basically everything will just grind to a halt. Don't do that. But what you can do with this kind of stuff is, and what we do in Netty, we run with this leak detector level every CI build. And if some leak detector report pulls up, we basically fail the build. So that's super handy for this kind of stuff. You can even adjust it on runtime. So you can do like write a JMX, whatever thing, and adjust it, enable it in production if you think there's something going on. So this really helps to get you a better idea about where the leak happens. What we also do is now we use direct memory by default. So all the allocations in Netty are direct by default. You can also request heap memory if you want to. We also have methods like, I don't know, get an unsigned in, get an unsigned bind, and all that kind of stuff, so you don't need to mask it by yourself. So there are a lot of different methods that you can take. You can write bytes, you can write an array of bytes, you can write a byte buffer, all that kind of stuff. So we have a lot of methods that we basically expose that are very, very useful. I think most people that used byte buffer before needed something like read an unsigned in at some point or read an unsigned byte. We provide everything like this. So the buffer pooling. So to give you a better idea about why it matters, so here's a diagram. This was done by Twitter. So it's on a Twitter blog post in the engineering blog. So Twitter is using Netty as well with Finagle, so they are big users. So here we basically benchmark the different number of nanoseconds for allocating, deallocating. So all the time just allocate, deallocate the same buffer with different sizes. So first off with 0. So why does it even take time with 0? Basically because of the overhead. I mean, we have a wrapper around the memory. So you see there's a different, and with different sizes. And I would just pick, for example, the biggest one, because you see as bigger as the memory sizes go, as more is the effect. You see allocating a pooled, direct buffer is like 3 times the time faster than allocating it unpooled. So it makes a lot of difference. And if you benchmark your application, you will see it, even in the profiler, to show up. But it even may make a difference for do that with heap buffer, and that's why we also support pooling heap buffers. You may think, well, why does it matter? It's just a byte array, right, which is wrapped. So the problem here is, or I don't know if it's a problem, but the JVM or Java itself, as part of the specification, it's defined that they need to zero out the byte array every time you allocate it, which is not for free. So if you have a very self-contained application, you may not want to do that. You just may want to use the same memory all the time, because also if you write C, you don't do a memset all the time to reuse a byte array, right? The same is true here. You can use either pool both, none of them, all kind of stuff. It's all configurable. And this is how it works. So if you ever, well, looked at jmalloc, it's basically jmalloc 3 in Java. So jmalloc works like this. So there are multiple threads, basically, that may want to allocate. So first off, if they try to allocate, they look into a thread cache, which is thread local, basically, in Java. If there's memory or buffer already in the right size, I will just pick it from there, because then I don't need to do any synchronization, right? It's just the same thread, basically. If there's nothing in there, I will go to some arena. They call it arena. An arena is basically like a tiny, small allocator by itself. So there are multiple arenas. How much of them? You can configure them. In Netty, it's basically like 2 times cores by default. So it's chosen randomly per thread and never change. Go there, try to allocate something in the arena. The arena itself has different size classes. So you have like, if you want to allocate something which is 32 bytes, you can allocate it from a size class which can be used for allocations up to 64 bytes. If you want to allocate 256, you go to a different size class which support up to 512, for example, and so on and so on. You can configure a different size class as well. So it's super flexible. It may happen that 2 threads use the same arena, which means that basically at this point they need to synchronize, right? And that's why you have the thread local caches. If you want to read more about this, there's a white paper in jmalloc. There's a blog post by Facebook about jmalloc, because the guy that wrote jmalloc works at Facebook. So if you want to know all the details about this, you can read this. The J in jmalloc doesn't stand for Java. It's Jason Effen, it's his name from the guy that wrote it. So that nothing to do with Java. It's the default allocator for FreeBSD these days, so it works out pretty well. So if you want to read up on this, go on the internet. You can do it by yourself. So the threading model. I talked about this a little bit before. I just want to show you some diagrams about Netty 4 to make it a little bit more clearer. So here's the channel. The channel is put on an IO thread, which is the event loop. It never changes, which is a good thing. So you always know the same thread is operating on this. So you don't need to have any volatile and all that kind of stuff. Then the IO thread basically fires event to the channel inbound handler, channel outbound handlers. So this really enables you to don't care about synchronization at all, because writing multiple threaded code is very hard. I mean, it's very hard to get right. The only time when you really need to care about this kind of stuff is if you have channel handlers that you share between different channels, because different channels may end up on different threads. If you don't have an event loop group which just have one thread, which makes sense, I think. So if you have a handler that, for example, counts all the connections, that needs to be thread safe because you share it. But if you have a handler which is only used in one channel, you never need to care about synchronized. And how does it work? If you call something from a non-IO thread in Netty from outside, so you call channel write basically from the outside, we check, is thread current thread the same thread that sits under the event loop of the channel? If not, we basically schedule it on the event loop. The event loop itself is just an executor, basically, in Java. And the same is true for writes and reads. We changed the write semantics in Netty 4. So Netty 3, every time you call channel write, if it ends up on the socket, basically we do a socket write, which may make sense. The problem really is that people tend to do channel write with very, very small buffers, because every time you do it when you have something, like if you have, for example, a byte output stream, you call write multiple times, right? So we were thinking about how we can improve that for the user. Because, I mean, in POSIX, there's something which is called write-ev, which is basically a syscall which allows you to do one syscall and write multiple buffers at the same time, which is a lot cheaper than doing multiple syscalls, because syscalls are expensive for multiple reasons. First off, for this in Java, you need to basically go from Java to C through the JNI layer, which is expensive. And then in C, you do a syscall and go from user space to kernel space, which is also expensive. So you don't want to do too many of them. So what we did in Netty 4 was basically, the idea came from someone from Twitter that worked there, from Jeff Pinner. We decoupled the writing and the flushing, which was one before in Netty 3. So what we do in Netty 4 now, it's more like what you do in an output stream. Basically, when you call write, it may never end up on the socket. You need to call flush. If you call flush, you're guaranteed that everything that sits in the outbound buffer, we call channel outbound buffer, will get written to a socket at this point. Which means you can do a lot of interesting things. It comes in pretty handy if you have protocols which, for example, supports pipelining. So if you write an HTTP server which supports pipelining, what you can do now is basically every time channel read is called, which is when something inbound happens, you call channel write with a response. Then we have an event which is called channel read complete, which basically said, now I'm not able to read anything more from this channel. This one is triggered, then you call channel flush, and everything that was written before is just written in one syscall. And we benchmark this, and the performance difference is 35%. If you write a lot. I mean, it really depends on how often you call write. But if you do pipelining with, I mean, you can do whatever, like 1,000 pipeline requests, it makes a huge difference. Here the catch is that you may not be able to write everything because you may exhaust basically the network buffer that sits on the OS. But we know basically when we write as much as we can. If we cannot write everything, we basically register ourselves on the selector, epoll, KQ, whatever it is. And once it becomes writable again, it gets woken up. It knows how much it needs to write because when the last flush happened, and we write the rest. So it's really non-blocking, everything like this. The only downside with this approach is basically that you need to be careful to call flush at some point, because if you don't do this, you end up with a lot of stuff in memory, right? But to help you with this, basically, we provide support for back pressure. So we have something which we called channel writability changed event. So every time a channel goes from writable to non-writable, and vice versa, basically, we fire an event and you can check, okay, now the channel is writable again. I will continue write. Now it's not writable again. I will call flush and this kind of stuff. And all of this depends on which settings you basically do on the channel, how much bytes you want to buffer before a channel becomes non-writable. So it's super flexible. You can even do more interesting things here. If you build, for example, proxy applications, you can even say, well, now the outbound channel from my proxy application is not writable anymore. I will stop reading until it's writable again. So you can build back pressure from basically two sockets which are piped together. That leads me to the read semantics. So in Netty 3, basically, what we did was every time new data comes in, we just fire off read events. So there was no easy way to basically say, I only want to read one time. It does it all the time, well, in a loop. You could do something like set readable false. Then it stops, but you don't have good control how often it will call it before it stops, actually. In Netty 4, what you can do is basically you can set something like set auto read false, which means you're responsible to call generate each time you're ready to read more data. That doesn't mean that something will be read exactly this moment. It's more like, now I'm ready to read more data if there's something there. So you can really, you can bridge something like reactive streams on top of Netty, where you basically say, each time there's a request to read some objects, I will just call generate and stop doing this once basically the subscriber cannot take it anymore. That's basically also how the reactive streams adapter on Netty is working, basically, which was done by Lightband or TypeSafe, or I think it's Lightband now, which is also used by Play. You can even set how many messages per read loop you want to do, because if you would just keep on reading everything that is on the channel, you may get a problem if you have a very, very slow remote peer, because you share the same thread with different connections, right? If it just fills in the buffer every time a little bit until you get it read, you will never stop. We also have like a received byte buffer allocator where you can basically say like, this is my best guess how much memory I want to use, and this is the buffer I give you. So there's a lot of flexibility that you can do. I/O threads. So I talked a little bit about I/O threads before. So basically these are the threads that do all the I/O and event processing. It's abstracted as event loop, which is nice. In Netty 3, basically there was no like global abstraction. Here basically it means you can use the same thread for a server and for the client. Why is this interesting? For example, again, if you build a proxy application, you can use the same event loop of the accepted inbound socket for the outbound socket for the remote host, which means you can pass data from one socket to another without a context switch. By the way, in the native transport, we also support splicing, where you can basically just splice from one socket to another without leaving kernel space, which is super nice as well. That's even cheaper, but you cannot basically transform data in the user space anymore. The event loop itself, it extends event executor, and event executor extends scheduled executor service, which means you can schedule events on the same thread that process the I/O for a channel. Why is this useful? For example, if you do a write, you can schedule an event and can say, if this write doesn't finish in 5 seconds, close the connection, for example. And again, you don't need to worry about synchronization because it's the same thread. So it's super handy. The only problem sometimes here is that people say, okay, it's an executor, so we'll just do something blocking here. Don't do this, because if you block there, you block everything that sits on the same thread. It's non-blocking, right? Well, sometimes you need to do some work out of the I/O thread, because sometimes you need to block, because maybe you need to call some API which doesn't support non-blocking, like JDBC or whatever, or the file system. There are a lot of APIs, especially in Java, because Java was not built with asynchronously in mind, right? So there are a lot of APIs which are still blocking. For this, we provide something which we call event executor group. So the event executor group is the same like an event loop. Basically, you have multiple threads which process stuff, so it's also just a thread executor, or well, thread pool, basically. The interesting thing here is basically that if you build up a pipeline, in the pipeline you put all the processing logic, like different handlers to process like bytes and put them to POJO, business logic, you can specify as well an event executor. Which means if I want to handle something in this handler, do it on this event executor. Which means basically you can move stuff from one thread to another, which is the event loop, for example, to an event executor. You can even say, well, for this handler I want to use this event executor, for this handler I want to use this event executor, and for this one I want to go back to the event loop. So you can do all this kind of different things. The same is true for event executor as for event loop. Like I said before, it's also basically extending scheduled executor servers. So you can also schedule on this. We have different implementations. The default implementation basically also preserve order for you. Because the problem is if you have a protocol like HTTP, even if you offload stuff to a thread pool, you need to preserve order for the responses, because it's not expected to basically, if you do 2 requests, to first answer with the second request. We do all the ordering for you. If you don't care about this, we also have an unordered event executor group, which could be handy for Datagram, UDP, because you don't care about this kind of stuff. Or for example, Cassandra is using this. Cassandra is using something like this because they already have their message, their POJOs basically, which are their CQL whatever messages, and they don't care about ordering there anymore because they will just multiplex them on different threads and put everything together because they have a message ID. So you can do this just with Netty without any extra work. JNI-based SSL Engine. So most people still think if you want to do SSL, you cannot terminate on Java because it's slow, right? It's kind of slow. If you use the JDK implementation, it's slow. It's not as slow as it was before. So these are the worst case numbers that I show you here. So for most ciphers these days, when you use Java 8 update 60 or later, it's kind of fast. So it's half the speed of our implementation, which I talk about now, after I showed you the numbers. So here I did a benchmark, which basically is using WRCAR, which is like a HTTP benchmarking tool. Fired up an HTTPS server, except basically just hello world, like the teach and power benchmarks, basically. I mean, it's a very, very primitive benchmark, but it just shows you how much you can push. So with the SSL Engine implementation, I was kind of be able to do almost 150,000 requests per second. Well, with our implementation, which is based on OpenSSL, with JNI, I could almost do 500,000. So it's a lot faster. Another very interesting thing is because we are using OpenSSL or LibreSSL or boring SSL, whatever you like. I mean, it's the same API. We also support ALPN and NPN out of the box, which means you don't need any hacks to make HTTP2 work, which is a very, very big pain point with Java 8 still, because you need to use like the boot class path hack, for which is supported by Jetty, for example. So this will just work. We provide support for different operation system. Just let me show you the CPU before, just to give you an idea. So the right side is the SSL Engine implementation, so it's kind of idling on 24 core box. Left side is the OpenSSL Engine, so basically it's just melting down, which is the right thing to do. With a newer JDK build with some ciphers, it looks almost like this as well. It's just half the speed. It really depends on the cipher. They just changed it in update 60. So if you're on an old build and use SSL and use the JDK implementation, update. It's faster. So the OpenSSL Engine, like I said, it's a drop-in replacement for JDK. So these days we support server-side, client-side, SNI, all the ciphers that basically JDK support, plus the extra ciphers that OpenSSL or LibreSSL or boring SSL supports. Gives you up to 6 times the performance. I was not able to get the JDK implementation faster than half of the speed than the OpenSSL one. So even in the best case, it gives you like 2 times performance. It has less memory usage because of how the caches are managed by OpenSSL itself. Less GC because we don't need to create all the extra objects which the JDK one does. If you want to switch from one to the other, you just need to change one line of code, basically SSL provider JDK or OpenSSL, depending on what you want to do. If you don't specify this by yourself, Netty will just detect if you have the OpenSSL jars, the module basically on the class path. If so, it will use it. If not, it falls back to JDK, which means you can basically just write your code. If you have the OpenSSL bindings, it will be faster. If not, it will just work. It's just slower, which is nice. It's the same API. You can even use the OpenSSL engine without Netty if you want to. So if you don't want to use Netty, you should use Netty. But if you don't want to use Netty, you can just use the OpenSSL engine. And it's based on Apache Tomcat native. Twitter forked it at some point, then basically open sourced it, contributed to Netty, and now we have our own version. So in the last 5 minutes, I want to talk a little bit about the JVM and Netty itself, and why I sometimes need to hate the JVM. I mean, I really love Java and the JVM, and I think it's an awesome engineering work, the JVM, but sometimes it just comes into your way. And I want to show you a little bit why. Maybe for most of you, it doesn't care too much because you only need to care if you do a lot of performance stuff and really low-level stuff like network programming. Direct memory management. I talked about this a little bit before. So direct memory management is done by the JVM by using finalizers or a cleaner or whatever. And I think this just doesn't work. Because of the reasons I told you before, because the garbage collector basically runs when you run out of heap space, right? So I don't think it's the right abstraction. I see why they did this, because, I mean, it's just the way how you develop Java, because it would be very strange for people to basically say like, oh, now I have direct memory and I need to release them, right? Because you don't want to do that in Java, but I think it's very bad for the performance if you write network application, because most of the times you have a very good handle about when you want to release the memory, because you want to release it basically when you wrote it to the socket, right? You have a pretty good handle about when you can release memory. And that's why we basically do it in Netty. The memory layout. Sometimes the JIT just tries to be too smart. I mean, most of the times it makes a lot of sense because it tries to basically get you the best out of performance and memory usage, right? So the JIT may rearrange files inside of your class because there's some space in between, so it doesn't, well, basically lose too much memory and all that kind of stuff. But sometimes you know what you're doing, because you can get false sharing. I don't know if you know about false sharing and what it is. I think it's more known from people that do C or C++ or something more low level than Java. Basically, what false sharing is you have two objects, two memory, well, pointers or whatever, which are sitting on the same cache line, and you access it from multiple threads. And because multiple threads using the same cache line, you play ping pong to update between them, because you need to basically refresh their view on the memory that they have, which can have a very, very bad impact on performance. And it's very hard to basically see this, why this happens. I mean, just to debug this, you need to look at the hardware counters and all that kind of stuff. So it's very, very invisible from Java. To help with this, what you can do in C is basically you can add padding. You can say, here's a struct, and I want to have the struct laid out exactly like this. And the GCC or whatever you use as a compiler will never touch your stuff to readjust this. If you want to do the same in Java, basically what you are doing here is, well, you may think, well, I could just use the fields and just put it like this, but the JIT may just rearrange this for various reasons, like save memory. So what you can do in Java here is, and that's basically what, for example, GC Tools does, which is a queue implementation which we use in Netty. It's a very awesome project. So if you want to use a queue which has some very, very specific access pattern, like multi-producer, single consumer, you should use something like GC Tools and not the JDK ones, because it's a lot faster. The JDK ones are always multi-producer, multiple consumers to make it safe to use. But if you know what you're doing, you can get a lot more speed with GC Tools. So what they are doing is basically, well, to prevent the JIT to do something stupid, well, okay, let us try this. So I will just arrange them how I want them. Okay, that didn't work. I will make them public, because then it cannot optimize it away. Well, that didn't work out too well as well. I make them public volatile to say, well, it may be accessed by multiple threads and you are not allowed to do anything. That doesn't work as well. It did work at some point in time. It doesn't work too well anymore. So you start to do, okay, I will pad them by myself now. I put like 8 longs before it, because 8 longs are 64 bytes, which is a cache line, and well, that will work. It doesn't work because the JIT will rearrange the files. So we say, okay, what I'm doing now, okay, so now comes the ugly part. You create a class. In the class, you start to do only the padding, then extend this class, add your file there, then extend this class, do again a padding, because you need to pad before and behind, because otherwise you may share a cache line again. Then you add your other stuff, and so on and so on. So you get like 20 classes to extend each other just to do padding, and that works. It's an implementation detail. It may not work in some update, but it works for now. So that's super painful. And I would like to have more control over this if I know what I'm doing. And object layout may change this to some extent. JNI, to make JNI work, sometimes you need to have nasty hacks, like pass memory pointers directly, because otherwise it's just too expensive. I mean, there's just a new talk to include a new standard for this, to improve JNI, but it's super expensive. I mean, especially if you go from the C layer to Java layer back, if you need to call back into this. So I hope this will change a little bit. I don't have too much time, so I will just move over this. NIO, NIO2, basically, I don't think it's it's a very good improvement over NIO, because, I mean, I think there's not too much in NIO2 which is good enough to use it, compared to NIO. I mean, there's the files abstraction, but that's it basically. For the rest, you can just use NIO. It produces too much garbage. For example, the selector, the key set, it's backed by a hash set, which means every time you need to access it, you create a new iterator, a new hash set, you can create garbage, all that kind of stuff. All the Java frameworks that I know that care about performance basically use reflection to inject their own implementation to reduce garbage, like Aaron, like Netty. So hopefully that will change at some point. Byte buffer API is not very user-friendly. There are no special exceptions for connection reset events, so you have no good idea about if it's really a hard problem or not. Java util concurrent future is blocking by default, which I think is against the design of a future. I mean, completion stage is a little bit better in these terms, but it's still a problem because it extends future in some point, the complete with future stuff. So there's a lot of stuff, I think, that could be changed to make it easier and harder to shoot yourself, basically. So the last one, before I'm finished, Make Me Rich, buy my book. You need to buy a lot of books to make me rich. So buy a lot of books for your friends, for your wife, for your husband, for your kids. Kids love network programming. So just buy a lot of books and make me rich. So yeah, that's it. If you have questions, I think the time is over, but it's okay. No, it's over. Okay, if you have questions, I'm here. I'm around a little bit. Just catch me up, and thanks for your time.